How's it going, everyone? Welcome. Javier Gonzalez here again. And today let's going to explore now the recursion, especially this advanced technique when it comes to break down a complex problem into small chunk one, or as I would like to call is, I have this problem that I could solve, and then this concrete problem that I can solve, and so on and so forth, whether it's in an iterative approach or in a divide and conquer like. Now, it is important to know how to describe these particular problems in terms of what is the recursive way of how you can describe a problem like this. All right. Most of the time you can solve this in an iterative approach, but the thing here is that this technique that most of the time they don't see the production because there's some uh, stuff that can happen, especially something called like range errors. When you call too many functions, or when you add all of these functions into the call stack without any stop condition. So, because of this recursion, which is a technique that, despite that it's not being seen too much out of the wild or in production, it's still important to solve specific problems, right? So, because, for example, when we're talking about here trivial examples like count vowels, where you say, hey, given these huge collections of characters, how can I now solve these particularly problems in terms of count the number of vowels here? And the another is how can I make if a particular string is a paragraph of an anagram, uh, giving a base condition. The TLDR of all of that is that with recursion, you have now this skill that the idea of this is to look now at this bigger problem and then break down into small problem that you can solve, and do that over and over and over. Now, we look at how can we solve these particular problems, especially like counter vowels and some other conditions as well, and especially the anatomy of the recursion when you describe is the uh, recursive way or the base condition or the stop condition that you want to do this function call, because at the end of the day the nature of recursion is that it's a function that calls itself and in itself and in itself and in itself, with the aim to solve now a small piece of problem, a small chunk of problems at each of one of those calls. So by the time you reach to the base condition, then you can now is uh, you already solve that particular problem. So he will look more for an optimization techniques of when you need to locate the base condition, and even though that we also look at a particular exercise here, oops, which is with recursion, recursion here. Right, this is an example of this. Let me put it here, a recursion exercise. Right. So recursion exercise here. It's a recursion exercise, like so, right? Recursion exercise. uh, we went through look and explore what is this recursion is all about, because anytime you do a function call, what's going on is that it's creating now a stack frame. In other words, it's just a space in memory that needs to keep track of the local variables as well as the variables that are closing over that, and it's going to do that over and over and over until we reach to some base condition or the stop condition. But because this, and here we're going to talk about the stack frames and memory limits. So this is not stack frame and memory limits, right? Stack frame and memory limits, which is part of the discussion in today's video, right? Stack frames and memory limits. Because doing this or letting now the JavaScript to at some point be able to crash the device, because when you don't have that enough memory, your device will crash. So you can think of this as, if you don't have any memory or any empty slot in your pants to put stuff, keys, or any other stuff that you might need or you might need to carry on, well, it turns out that you don't have any place, so therefore you get stuck. What you can do is to, well, try to figuring out what are the stuff that you need to throw away, to drop. But the TLDR is that in the computer science, once it's reached the limit, then you can actually is denial a service. And this is part of this is a problem, because you can is cause a denial of service by only running a function called without a base condition. So functional programmer actually know about this, and then because now JavaScript is running on the browser, so the browsers developers in this browser the browser vendors and the browser developers actually now make a fixed amount of function call that you can do. This is also something that Internet Explorer, for those who are not familiar with, I actually dropped my password in DNI in my birth date as well, because those in that era, sorry, because in that era, right? Sorry, because at that time, well, that was an arbitrary number that some of the developers at Internet Explorer actually come in and they say, hey, 13 is the number of maximum call size you can do. But now this has changed and evolved over time. So this is a very interesting question to know what is the range of how many times you can call a function here. And you say, hey, how you can actually do that? Well, let's do this. Say a recursive counter, right? Recursive counter. It doesn't receive anything. All right. And we just want is to return a function, all right, where I want to call this function, and then now say, hey, console.log, say console log here, it'll be now count plus plus, right? Count plus plus. What you can do is something like this, right? So I prefer to increment first and then assign that. That'll be preferable in this case. It's gonna go with claw here. Gonna go with claw here to actually check that. So the difference between plus plus, counter plus plus, and counter plus plus in JavaScript. To the value being returned. So the pre-increment is say the counter is increment first, then the value is returned. So returns the new value after incrementing. So this is something that you might want to do. And this is the original value is returned first, and then the counter is incremented. So return the original value before incrementing, and the incremental happens after the expression is evaluated. So in this case, it will be 6. In this case, it will be 5. All right. And on the next call, you're going to have this. Right. So, but it's all about is assignment when the assignment is happening. So because we don't have any counter here, we just can say, hey, what you to now define is a variable here called counter, right? Or to be much more easy to go with, let's gonna define as a count, right? That initially will set to 0 if you don't pass any value. And then we want is to call this as expected, right? We want to call this function. We want to say, hey, I want to call this and say this is the recursive counter. All right, then I want to, oops. And then I want to is return the call, right? By saying is recursive counter here as is. So because here the counter needs to be incremented at any time, right? And because this actually increment the counter here, so we can say something like, so we can say something like its recursive count is equal to 0, right? So here we prefers to say, hey, I like to define now a counter here with 0 initially, right? And anytime I run this function, which is also something that I can say like this, and anytime I call this recursive counter, I want to is do something like this. I want to show the count, how many times I'm passing this, and then pass now the counter as it is. So I want you to is first increment that counter and then return its value. So, oh my god. So this is the count, right? And then I say increment its value first and then count. Okay, good. And when it comes to call this, you say a recursive counter, and it's like this. I want you to assign this to a function variable, or a const that is recursive counter. It's going to say is recursive calls. Okay, and then I want to do is this, say recursive call to see how many times this will be allowed. Recursive counter is supposed to call this again. Oh, I get it. It's because I need to do is as it is, right? I need to do is as it is. Yep, just like that. So in this case, I'm just evaluating like this, right? Anytime I pass in a counter, there will be 1 and then 0 and then so on and so forth. So if we do this, we can see is that now it's actually telling us is how many times you can now call this function, or in other words, how many frames can you add to the call stack. And this frame is a technical term to say, hey, this is the function call. In other words, the space in memory that I create for this function that will contain this particular information, all right, which is like this. It will contain this information. It will contain a parameter that initially is 0, and then the other one like so, right? So what it's doing here is that we are using is this inner mechanism that JavaScript or any programming language that actually allows you to have now this recursion, this function that called another function, another function, another function, or a function that called it itself, and once it reached to a base condition to solve a particular problem. The thing is that when we learn about this, most of the time we do that from the implementation details, which is something that is not helpful because, again, at the end of the day, with recursion, all we want to say is, can we now describe a particular problem by breaking down into small chunk of pieces? So I have this problem that I need to solve at some point, this large problem that I need to solve, and then I concretely solve this problem. So why am I doing this? Because this is a way of how you can see that browsers like Brave, in this case, which is an instance of Chrome. If we take a look at now another one.
No, marico, busco otra opción, weón, pues imagínate, vamos a quedar yo en Ciudadela con 2.800.000 pesos en efectivo 1 hora esperando que llegue. No hay chance.
So for example, in browsers like Firefox, okay, it is interesting. Now things change a little bit. It allows you to do is 27,000 function call. Interesting. So imagine that you have now a stack of 20,000 paper, right? Each one of another. You know, and this kind of exercise is important to do because it now gives you a sense of what recursion is all about, and what is this tool that we put in our tool belt to see how can we now try to solve specific problems, particularly problems where we don't know is the length of that, right? So this is, for example, when you talk about is now traverse a particular data structure, that you don't know the length of the data structure beforehand, right? Unlike arrays where you know that this is a fixed size, right? Because you need to define that dimension first. But for data structures that are more flexible, like linked lists, trees, or graph, that you need to iterate through all of the elements on that data structure, it makes a lot of sense to use now a recursion technique. Okay. So this is interesting because in JavaScript, right? And depending on the browser implementation, and let me actually put it this, bro. So stack frame, memory limits. Browsers, so browser like, let me actually test this on Chrome. Okay, I'm gonna test this on Chrome. Wait, what? Okay. Interesting. Okay, okay. So that's interesting because now browser based on Chromium, it allows you to now run is up to 80,000, which to me, of course, is because browser vendors are scared of the users. That's what happened. So browser vendors are terrified of their users and what they can do. Let me put it here, a screenshot here. Until we finally get is this range error, right? As you can see, is this one. And another one is from Firefox, right? Which is an interesting way to do this. Too much recursion, right? So anytime that you look at too much recursion, is that somehow some function is calling itself, aka is now adding all of this stack frame on top of the call stack in an indefinite way. So the browser, to prevent the browser crash, it fixed the limit to that point. So this is what we're gonna write here. So browsers like Firefox, okay. So browsers like Firefox it's at the cover letter. Where it is. Exactly. So for browsers like Firefox or Chromium base, this is not. Is this one? Since any time you call a function in a exactly, so anytime you call a function in JavaScript, it creates a space in memory known as the stack frame. Okay, it creates a space in memory known as the stack frame. So the computer doesn't know about the idea of a stack. This is something for us as human to understand. Exactly, this is all for human to understand how that thing is working. Okay, this is something for us. This is something for us. For us, humans, to understand how that thing is working. All right. So the idea of a stack. So the idea of a stack, pretty much like you put several pancake. Yes. So you put several pancake. Oh my God, pancake. One over another. One. So you put several pancakes, one on top of another, one of top of another, and another, right? So the idea of a stack pretty much is like you put several pancakes on top of another. But in JavaScript, each stack contains information about that function, and it is surrounded. So surroundings, right? It is surroundings. surroundings, surroundings. Okay, and it is surroundings. All right. So far, so good. Because browsers are scared of what end users might be doing, they set a memory, or they set a limit of how many functions. Okay, so they set a limit of how many times a function can be called, aka reserve space in memory for that stack frame, to prevent the browser from crashing, and some other denial of services. Right? So that makes a lot of sense. This is huge, by the way. Huge, 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 huge. What French stuff is this? You got it.
So let's talk about recursion in the practical sense. We can get a sense of the theoretical way that this works. But in the practical sense, many of you probably know that recursion often doesn't make its way into production applications for one particularly sticky reason, which is that range error that we get thrown whenever recursion has been running for too long, and we get a range error thrown, stack overflow exceeded. Okay? That's the major problem that I think for the last 50 or 60 years has essentially limited the utility of recursion from being a general programming thing that everybody has to learn and everybody has to use, is because a lot of people basically think in the back of their minds that sort of nagging feeling like, yeah, it sounds good in theory, but in practice it would probably blow up, so I'm not going to use it. And so I want to talk about that because there are ways of addressing this problem. In theory, your computer could just run forever. And
So because this is a technique that is not seeing the light too much in production, because of the range error that developers say, hey, this is good in theory, but I want to save myself in practice.
and you'd have infinite memory and infinite CPU, but in practice we know that's not the case. And so we do need to actually step in. A little bit ago I said, try not to think too much from a computer science-y perspective about what's happening in memory. But to get an intuition for why there is a practical limitation problem, we do need to think just a little bit about the implementation side of it. Okay? I don't want you to think about implementation as you're authoring this code, but it's just to get us a sense of the problem of the range error, of the Stack Overflow problem. So if we think about when a function gets called, when one function is running and it calls off to another function, it doesn't have to be its own function, it doesn't have to be recursion. It's just the general problem that when one function calls out to another function, at that moment, everything that was currently happening in that function needs to get saved somehow so that all the stuff that happens in the other function doesn't mess up what was happening in the first one. So if you're in the middle of function A and you call off to function B, you kind of have to have somewhere where all of A's in progress work is saved so that there's some place, a scratch pad, if you will, for the work for B to happen. And in computer science terms, we call these stack frames. Every time a function gets executed, an area of memory is reserved, and it's called a stack frame. And we call it a stack frame. We actually call it a memory frame. We call it a stack frame because when one function calls another, and then that one calls another, and that one calls another, what we have is a stack that's growing. You have at the bottom level the initial function that called off to B, and B called off to C, and C called off to D. You're building up a stack. And we use the stack data structure idea because when this this topmost function, if you will, finishes running, and its work is done, we can get rid of that memory, and we pop the stack back to the previous one, and it picks up where it left off, and then we pop the stack back to the previous one. And it might call another and another and keep coming back. So we have this stack data structure. Whether or not the computer actually uses a stack, conceptually, it uses a stack to manage all of the work as it builds up and goes back down and builds up and goes back down. So what kinds of things are in these stack frames? Well, you have all of the local variables that have been assigned, any memory that's being assigned for those. You have the program counter, which is basically what line of code it's on or what part of an expression it's on or something like that. So basic things like that, very low-level things that the computer needs to track what's happening inside of a function. And it doesn't take up a lot of memory. We're not talking about like megabytes worth of memory. The stack frame is probably like a few hundred bytes or a K or something. It's probably like a couple hundred bytes at most for each stack frame. And if you're calling 100 functions in a chain, which almost never happens, by the way, probably at the most you probably go 5, 10, maybe 15 deep. But if you've called even 100 of those functions and you've still only used up a fraction of a megabyte of memory, it's not a big deal. You never see any sort of a problem with that. But as soon as we get into programming practices like recursion, it becomes dramatically more likely that that stack frame depth might grow to thousands, tens of thousands, hundreds of thousands, millions, and even beyond. And that does start to chew up some non-trivial amount of memory. Now, this is not a new thought. This is not a new occurrence. Almost the day that recursion was invented back in the whatever 60s, the very next day somebody thought, oh, we only have like 4K of RAM on this computer. We can't do very many function calls in 4K of RAM, right? So back then they had much more of a pronounced limitation than we even do with our fancy gigabytes worth of memory. They had way less memory. So this was a very present problem for them. The math predicted that recursion was this great way of doing things, but in practice we're limited by the amount of memory that we can run. So they immediately had to confront, is recursion something that should just be filed away as a nice great theory but not something that can be used, or is there some way to address it? And the way to address it that they invented back then and has been this time-honored approach ever since is an optimization called tail calls. To understand what a tail call is and how a tail call works, we need to understand when we make this recursive call here, the call on line 4, we need to understand why the stack frame that is currently executing needs to be kept. What is it about that stack frame that still needs to be kept around? And in particular, the reason why that stack frame needs to be kept is because we are doing that first addition, the addition of the return result, after the function completes. So it's essentially that part of the program that's requiring our current stack frame to be around. But if there was no more work to do, if we literally just said return count vowels, and there was nothing before or after that, it just called the function and it was done, then we could think, at least in theory, that it seems like the current stack frame isn't needed anymore. We've done all of our work in our current stack frame, and we're going to dispatch to another function call, and so why don't we just maybe throw away the current stack frame, or just reuse the existing stack frame for the next function call? You follow me? That's the idea here behind tail calls. If a function call happens in a position which is referred to as a tail call, meaning it's at the tail of the execution logic, it's at the very end of that function's logic, then we don't need the existing stack frame anymore, and we can essentially dispatch to another function call and not take up any extra net memory. Which means that function A can call B, can call C, can call D. If all of those calls happen in a tail position, then we've only ever needed one stack frame in memory at any given time. We don't have this runaway of O of n memory usage where every function call has taken up a new section of memory. And it's an implementation detail whether we create a new one and throw the old one away or whether we reuse. It's different under different situations. But the general idea is at any given time you should basically only need one stack frame. That only holds for function calls that have happened in a tail position. Now this is an optimization in the bigger sense of optimization. It's not actually a performance optimization. It's not actually faster. In some cases, it might actually be slower to do what we're talking about. So when people say optimization, they usually jump to thinking, oh, well, this is a performance, it's going to go faster. It's not necessarily going to go faster, and in some particular cases, might actually go slower. But it's an optimization in the bigger sense because we're optimizing memory usage. We're saying, let's not have runaway memory usage unnecessarily. Let's not keep all those stack frames that aren't needed anyway. Let's run in essentially fixed memory space, O of 1 memory usage instead of O of n. Okay? And it's important to understand that tail calls are an additional feature that the system, your language, your compiler, your runtime has to support. It's not, you don't get it for free. So you would wonder then, well, what about JavaScript? Does JavaScript have this? And for literally decades, people have been calling for JavaScript to have this tail call support, this memory optimization, so that recursion doesn't need to throw this error that says range error out of memory. And by the way, a little side note on the range error issue. That range error, stack overflow exceeded or whatever, that error is there not because you ran out of memory. A lot of people think that's what's happening. It's not an out of memory error. If you have ever had an out of memory condition in a web app, I guarantee you that what you saw was, at a minimum, the browser crashed. And if it wasn't the browser that crashed, the whole device crashed. Anybody ever had your mobile phone just like shut itself off and restart? And you're like, how is that even possible to just be like clicking around on Facebook and all of a sudden my phone restarts itself? Congratulations, that was an out of memory error. Almost certainly, that's what happens when the system completely runs out of memory, just throws its hands in the air and says start over, right? Just restart the device because I'm completely out of memory. And JavaScript knows that that's a really terrible idea to allow JavaScript programs to run a device out of memory, because it's a very clear sort of denial of service attack vector for somebody to run some infinite loop on a page and kill people's devices. Okay? So because we know that's a terrible idea, JavaScript essentially from the beginning has had a check in place that has said, let's not run so far that we are going to definitely eventually run out of memory. And that heuristic, that decision metric for how does it know if it's going to run out of memory, is more complex than you might have expected. It used to be really, really simple. So this is actually true. Back in IE6, there was a fixed limit for the number of function calls that could happen, and that limit was in succession. This doesn't mean total functions ever executed. It means in a chain, where one is called the other. The total stack depth was limited to 13. I don't have any idea where they came up with that number, but if you ever had a situation where you called to that 14th call in a chain of function calls, you would get the range error in IE6. Somehow, some way, they thought 13, maybe they had a heuristic that said nobody ever goes over 13, and if they do, it's almost always recursion. I don't know. But anyway, it was limited to 13, which is ridiculous, right? That's ridiculously low, because that's like probably less than 100K of memory, way probably less than 100K of memory. So, how many function calls should it allow? This is sort of a weird kind of a prediction, because it's essentially the engine needing to say, this looks like you're probably going to run them out of memory. You can't actually know if the recursion is just about to finish. There's no way for the system to predict that. So it's got to run basically a heuristic and say, I think this looks like you're running a lot of memory and you're probably going to run the system out of memory, so I'm just going to stop you. That's the heuristic, and it's more complex than you might realize. Luckily today in modern browsers, it is much more sophisticated, the way they decide this stuff. I don't know exactly how they work. I don't know if it's like monitoring the amount of available RAM at any given point or something. But in my general testing, I've seen somewhere around 20,000 in the V8 JavaScript engine on my Chrome instance. I don't know if it's different for V8 on different devices or whatever, but I've basically been able to get up to about 20,000 stack depth before I generally see that range, or sometimes 21,000. It's somewhere in that range. So your mileage literally may vary there. You may have different results when you run it, but it's pretty easy to set up a test. Just write a recursive function that'll just print out an I and then increments and see how many I's print out, right? Or, that sort of thing. So the good news is that actually, on that topic of writing yourself a test, just put it in a try-catch so that you can see how big I was whenever the exception was thrown. But anyway, the point is, there is some sort of limit, and it's going to be different based upon the environments that you're running in. Based upon the device, based upon the browser, all those things, those are not things that you can predict or control. So that's what ups this ante for saying we need to have JavaScript support this idea of tail calls. And it has never done that. It has never gone to that level. And one of the reasons historically for not having that is because the idea of requiring tail calls was almost antithetical to the way the JavaScript specification was written. I don't really mean antithetical, but the specification is really deliberately designed to be as agnostic about implementation details as possible. It says, this is the final outcome that should happen, and it does specify algorithms for how you should go about accomplishing things. But if the end goal of any operation is preserved, the JavaScript engines, and there are many, there are fewer and fewer each day, but there are many out there. The JavaScript engines are allowed to decide, we're going to cut this corner and have this effect, and we're going to still get as long as we're spec compliant, we have a lot of leeway to do different sorts of optimizations to address things. So the Chakra JavaScript engine for Microsoft, back when they were running that, did things dramatically differently for the Windows operating system than, say, the Chrome V8 was doing on the Mac OS architecture, right? They're dramatically different ways of approaching those fine-level memory optimizations and things. So we have traditionally allowed a wide berth of choice in terms of implementation. And if the JavaScript specification steps in and says, you absolutely must throw away stack frames and allow O of 1 memory usage, all of a sudden that now starts to really encroach upon the space of these JavaScript engines, because there's almost nothing that JavaScript engines do that is more intensive from a resource perspective than function calls. So we're really mucking at the very lowest levels of the stuff that they're doing in their memory and their optimizations and stuff. We're really reaching far into their normal realm and saying, no, you have to do it in some specific kind of a way. So there's been significant pushback from JavaScript engines over the years to say we don't want tail calls. We don't even think people care about it that much. I've had conversations with developers at Microsoft, for example, that told me, well, nobody uses recursion, so why would we implement that feature? And my response was, nobody uses the feature because you haven't implemented it. And they say, well, nobody uses it, so we're not going to implement it. You can see the problem here, right? The catch-22. They don't want to implement something that's hard to implement unless people want to use it, and nobody wants to use it because it's not even possible to use. How are we supposed to resolve this problem? So I've been fighting, actually, this battle for a long time, trying to convince them, please do this sort of thing. Well, there's a proposal that came in ES6. This was back in 2014, 2015, when ES6 landed. There's a proposal that said, let's finally standardize that JavaScript engines have to do tail calls. Specifically, we called them proper tail calls. PTC as it's referred to. Now, just a quick note, there is a related term that if you do some Googling, you're going to see, TCO, which stands for tail call optimization. This is different. And for a long time, I actually thought they were basically the same thing. They are different. So let's make sure we're clear. Proper tail calls are the idea that a tail call gets memory optimized, that we only use O of 1 memory spaces. PTO, tail call optimization. Exactly. This is different. And for a long time, I actually thought they were basically the same thing. They are different. So let's make sure we're clear. Proper tail calls are the idea that a tail call gets memory optimized, that we only use O of 1 memory spaces. PTO, tail calls, are the idea that a tail call gets...
That computation, that whole function that happened at the end, that tail calls is the idea that the tail call is memory
optimized, that we only use O of 1 memory space, essentially. TCO, tail call optimization. Too many acronyms. TCO, tail call optimization, is a family of potential optimizations on top of PTC, which are optional that an engine may decide that it wants to do. For example, it may decide to throw away old memory. It may decide to garbage collect old stack frames, or it may decide to reuse a stack frame and grow its memory usage, or whatever. Those are this whole other family of low-level optimizations that essentially have absolutely no bearing on the JavaScript world. They matter to JavaScript engine developers, but they don't matter to us. Okay? The only thing that matters to us is PTC in the language or not? Exactly. Do we either get that members optimization and eliminate the range error or not? So the proposal was, let's standardize proper tail calls. And the language in the spec was deliberately a bit more open to essentially say, we're not going to require specific TCOs. We're just going to generally say that it should be possible for a function in a tail call position to be able to not take up extra memory. The language is more formal than that, but it's essentially a bit gray area-ish. It's not very fine-grained like you have to do the memory in this particular way. So the proposal was discussed at TC39 at length over a period of months. And sometime in 2014 or 2015, they voted, that is TC39, and that was present, all members of all the JavaScript engines, they voted to say, yes, let's go ahead and include proper tail calls in the ES6 standard. So here's what PTC was standardized on in ES6. Number one, you have to have strict mode on. It's not going to work if you're in the non-strict mode, sometimes referred to as sloppy mode. You have to opt in to strict mode to be able to do this. By the way, you should already be using strict mode in all your programs. If you're not, it's time to adopt that, because that's been around now for literally 10 years. So what are you waiting for? Let's get on the boat with strict mode. But you have to be in strict mode to be able to take advantage of tail calls.
Interesting.
Then you have to have your function call in what is called a proper tail position. It has to be a proper tail call. Now, the function call that you see here is in a proper tail position because even though there's an X and a 1, and we could even do stuff in the arguments, what you'll note is that nothing has to happen after that function call finishes except for its value to be returned. That's a tail call position. It is notable that without the return keyword, it is not a proper tail call. Even if it's at the end of the function, it's not a proper tail call unless there's a return keyword. Okay? Proper tail calls require a return keyword and a single function call and nothing else in that expression that needs to be computed afterwards. There's a slight little grammatical nuance there, which is if you have a ternary expression on your return statement and the function call is in one of the branches, that's a tail call because nothing else is going to happen. The ternary pre-computes and then picks one of the function calls. So that, even though it doesn't look like a tail call, that technically is. But otherwise, generally speaking, the pattern is you're going to see return and then a function call, and that's it, and that's going to mean that it qualifies as a tail call. This has nothing to do with recursion. This is just, it's a proper tail call, and the spec then says that the JavaScript engine has to make sure that no matter how deep that chain of function calls gets, you won't get a range error. It won't run the system out of memory. Of course, we're normally going to see this in the context of things like recursion, like this function here, which keeps dividing a number and calling it for several times. And those calls to diminish are proper tail calls. Even though there's math that's happening inside of there, the math.trunc and the x divided by 2, those are proper tail calls. Notably, math.trunc is not a proper tail call because there isn't a return before it. But it's okay because math.trunc doesn't call any further functions. So it's not contributing to the growth of the call stack. The thing that would contribute to the growth of the call stack is the call to diminish, and that one is in a proper tail call position. So theoretically, we should never have a growth of that stack, and therefore we should not ever have a range error memory, no matter how many times that had to run. Okay?
What would happen if instead of math.trunc, we had another function that calls another function? Like
that would not, yeah, that's a great question. So if that was a call that would contribute to the growth of the call stack, like if we were calling another function that called another function and created its own call stack growth, then that would definitely potentially grow the stack eventually to create a range error. So you only get the benefits of removal of stack frame from a conceptual perspective if the function calls are all in tail call position. So if you have some that are not and some that are, you're getting the benefit of the ones that are and not the benefit from the ones that aren't. It's the basic bottom line. So you do want to try to arrange everything to be in tail call position if you're expecting for that to happen. If you're in that fortunate position where you're writing only for Safari, then you can take advantage of this today. And hopefully, someday, you're going to be able to take advantage of this across all of the JavaScript.
But the idea is this memory optimization.
Let's go back to
the idea around
our
that,
example of count vowels. Remember this implementation from earlier in our discussion. And let's
Oh,
analyze that this is not in proper tail call position. How do we know it's not in proper tail call position? Because there is an addition operation that has to happen after the count vowels as well. So we know that those stack frames are going to be kept around. And the question is, that was the way we designed or solved this problem recursively, and it led to a non-tail call representation of the problem solution. So what do we do? Because in theory it sounds great for recursion, but in practice now we have this problem where it can't ever be optimized even if they ever implement proper tail calls. And the good news is that many forms of recursion, not all, but many forms of recursion can be reoriented to take advantage of tail calls, but it requires thinking a little bit more carefully about the problem. So this is a technique that you should be aware of, because if you are ever going to use recursion practically anywhere, even in Safari only, you're going to have to get comfortable with the idea thinking about proper tail calls, because it won't always be the case that your recursion nicely, cleanly is already in tail call position. You're going to have to probably put in that extra work. And sometimes you're going to be stuck where no matter what you do, you're not going to be able to do tail calls. There's a form of recursion called binary recursion, which is that you, and this is like what you see when you're like traversing binary trees, for example, where you call left and then you call right, and each one of those calls left and right. When you have a forked or a binary or even more n-ary sort of recursion, you absolutely can't do tail calls, because one of those is not going to be in a tail position. One of them might, but one of them isn't. And so you're just stuck. There's no way to solve that problem. You can't do two forms of recursion in the same function and have both of them be in tail call position. But most recursion that we do that isn't of that form, at least is possible to consider rewriting it into tail call form. So what we need to do is analyze, how do we get rid of that, essentially, how could we get rid of that first variable? Because that's the reason that it's not in tail call form. That's the reason why we need to preserve it, is because it's that pesky thing that's stuck there, it's hanging out there while the other function calls are finishing, and then we're coming back to it. So the key recognition point that is often going to lead you to being able to refactor something that's non-tail call into a tail call form, that key recognition point is to say, if I am keeping track of this information in the stack frame, that is my local variables in the stack, where else could I keep track of that information and not keep track of it in the stack frame? And there's only one.
Where else can I, okay.
That is my local variables in the stack. Where else could I keep track of that information and not keep track of it in the stack frame?
In a closure?
And there's only one other place that even makes sense. The other place that I could keep track of it in is in the next stack frame, aka the arguments that I'm going to pass to the next function. So instead of preserving a variable here, if I were to compute my response and pass it forward to the next function, then I have a place for that to sit. Instead of keeping my stack frame, finish all of my business and pass it all onto the next stack frame. And he finishes all of his business and he passes it onto the next stack frame and so on. That's how you refactor from non-tail call to tail call form. So what that looks like then is that we are going to want to reserve one of the argument positions for our running count. We could start that argument position out at 0, and then we just, each time we make the recursive call, make sure that that number has been incremented properly to hold that new value.
Exactly.
So this is what it might look like. We could call count values with the count argument and start it out at 0. We could pre-compute count like we were computing first before, but notice I'm doing a plus equals here, so I'm adding to count rather than recomputing only first. I'm basically making count bigger and bigger and bigger every time it's called, and then we're forward passing. And then you see on line 6, we pass in the new count to the next level of recursion. Now the problem with this is that it makes the signature of our recursive function more awkward. When it's a single number, like starting it out at 0, it's not a huge problem to tell people you have to pass 0, but it is a sort of leaky abstraction. Wait, why do I have to pass 0? Shouldn't you be taking care of that? So it's kind of leaking the abstraction that we're doing a recursion, that we're doing a tail call recursion.
Handle that?
So what you often will see is that someone will create an interface function that has a nice clean looking signature, and then they'll have the recursive function hidden away that has the non-clean signature. That's kind of the trade-off here. So what you might see is something like this. You might see a count vowels that we're going to store it in some place, and here's what I'm going to do. I'm going to store it in a curry. I'm going to create a count vowels that takes both of those inputs separately, and then I'm going to pre-specify one of those inputs down on line 7. That's a fancy way of showing you, that's a functional way of showing you that I'm going to store it in a closure somewhere. I'm going to store that information in a closure so that the call site that everybody else sees is the one that's only providing the second value. This is yet another example of using curry to our advantage. When we have some information that we need to store somewhere, curry takes advantage of, or allows us to store that information in that closure. So this is a common way that you might take a function written, like the one on line 3. You see I've written it in the sort of naive sense, but then I've presented to the outside program one that has a cleaner information signature where I only need to pass in the string. So now this count vowels function would in fact run. We can see the call site on line 6. That is the recursive call site, and we can see that it does in fact work as a proper tail call. It is in proper tail call form. We have strict mode. So if we were to take this code and try to run it inside of something like Safari and give it a really, really giant string that was millions of characters long, it would happily run through all those characters and give us a response. It would probably run a little bit slower than the for loop version because we'd have a million function calls instead of one. And there is some amount of runtime overhead. But we would at least not have a runaway memory situation. Because we know that proper tail calls aren't a thing that we can rely upon yet, we have to consider potentially other strategies for writing what are essentially recursive algorithms without having to rely upon that optimization of tail calls, at least in the interim. And I'm going to present to you 2 of these, and I'll just go ahead and tell you, the first of them you're probably never going to write, but it's important for you to at least understand that this technique exists. The second one is the one that I'm going to end up suggesting that you start doing today, because it works now even without tail calls, and it will gracefully gracefully progressively enhance to nicer recursion if we ever get tail calls. So the first of these is called CPS. It stands for continuation passing style. Okay, and just so you understand what a continuation is, that's essentially a callback. So if we say continuation passing, that means we're passing some sort of a callback. This is the CPS style. You'll notice that lines 4 and 5 of our function look basically the same. On line 3, we see something a little bit different, which is we see a variable there called called the identity function of stuff. Interesting trick. This is something that computer scientists and they've studied and figured these things out. And I'm sure there's a mathematical principle that allowed them to figure out if we'd defer it with a wrap function and that gets around this problem or whatever. That idea that I'm going to defer the work of first plus v until a later function call by wrapping it in a function, that idea we want to key off of for our last technique. This is the one that I want you to actually use. Okay? That technique is called trampolines. I want you to use trampolines because you're going to see that you write it almost as if it's just a regular normal recursive function. And then you have this adapter that helps take care of the whole tail calling problem. So what is a trampoline? It's a funny way of basically indicating that we want something to sort of bounce back and forth. That's why it's called a trampoline. So what is it bouncing back and forth? Instead of having function call function call function call function call function, our strategy is basically going to be function call function, return another function, then call that one, then return another function, then call that one, then return another function. And you can sort of visually get the idea of somebody bouncing up and down on a trampoline. So in other words, we never have the case where this thing is called this thing. We never build up a stack at all. The stack depth never goes beyond 1. Because what we do, instead of making a recursive call, is we return a function that will make the next call. That's how the technique works. So let's look at a utility for that. This is real simple. This would be provided to you by your functional programming library, and they're a little more sophisticated than this. But essentially, a trampoline function is just going to do a while loop here. And as long as you keep returning a function back, it's just going to repeat the loop again and call the function, and then get the result. And if that's a function again, it's just going to keep. So as long as you keep returning a function, it's going to assume you want me to keep going with the trampolining until the very end, when it just returns the result, line 9. It didn't get back a function, it got back a number or string or something non-function. That's how it knows. Now, libraries have a little bit more sophisticated than just a type of check on the function. So there's ways to even return back functions from recursion. But the point that I want you to get is that we're just doing a while loop, bounce back and forth. Call the function, get a function back. Call the function, get a function back, that sort of thing. And it can go forever because the stack frame never runs out, the heap never runs out, it only ever executes one function at a time. It's an interesting and unique sort of trick to the tail call problem. By instead of the way we solve the tail call problem is to just never have a stack in the first place. So what does it look like to use this trampoline utility? Notice that I've got to count vowels that from the most perspective, count vowels looks exactly like what we implemented before. I'm wrapping it in a call to trampoline like we did with memoize earlier in the course.
That function.
But the only difference, line 6 looks exactly like what we expected in the tail call form. The only difference is that line 5 wraps up line 6 in a function and returns it. That's the only intrusion that we have to do. Line 4 still looks normal. Line 3 still looks normal. Line 6 looks normal. The only difference to use trampoline is you have to take any call that would have been recursive and wrap it in a function and return it. And that's how you opt into this whole trampolining thing. And that function that we're creating, the function f on line 5, the way that function works is because it has closure over the stuff that it needed. So it temporarily, for a brief microsecond, holds onto those values so that they can be returned back to the trampolining utility, popping the call stack, and then it immediately re-invokes that and starts over. So we're taking advantage of the place that we store our information is in the return value of our stack frame, which then pops the stack frame off. That's how trampolining works. Now the reason I want you to start writing this form of recursion is because this form of recursion will be very easy for you and or a tool to automatically convert to real tail call form at some later time if we get to the point where tail calls are reliable in cross JavaScript. If you use a trampolining like this, all a tool would have to do is know that you use trampolining everywhere and go find those places like line 5 and 7 and just take them out. And then take out the wrapping around the trampoline thing. That's easily automatable by tools. So we can write something that is in tail call form, have a small little intrusion on it, and then automatically remove that at some point if we ever get to the point where tail calls are supported by the language. And if not, then our trampolining just keeps working, and we get all of the declarative benefit out of the recursion technique here. Even though this code is a bit more complex than where we started, it's still significantly more declarative than what we did with the iterative for-loop version.
It's keeping now a
this is my current state of the art, if you will. This is how I do recursion in my programs, is I write a tail call form and wrap it in a trampoline. But just like everything else I've taught you, you're not going to get to be comfortable with this sort of topic unless you start to try to practice it. So retry the exercises, try this stuff on your own code. Look for places where you're doing things iteratively and ask, is there a way that I could do that recursively? Could I use a trampoline here and do it recursively?
So CPS is some sort of memorization where we're trying to call const v.
If I go back to CPS for just a moment, I'll go back a couple of slides. In CPS, the trick is that what we're doing is instead of actually making the recursive call, doing the work now, we're deferring the work by wrapping it up in a function and passing that function forward. So none of that work is actually happening. You know how earlier we talked about do the work now and pass it along in a variable as an argument? Here we're saying don't do the work now, but pass along a function which will do the work later. And then that one passes along another function which will do the work later. So that cont variable becomes a bigger and bigger and bigger wrapped function. None of the inner functions have ever been called yet, but it's a bigger and bigger and bigger wrapped function, all of which are actually in tail call form. It's all a bunch of return, 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 return. none of the work has been done. What we made a bigger and bigger function with all that stuff closed over. And then at the very last thing, which is what happens on line 5, there's our base condition. We say, hey, big, giant, wrapped, huge function, collapse yourself down into one value. That's what line 5 does, is it calls that giant function, which computes all those values.
Why have tools to translate code to CPS if we still have the memory issues?
Well, we get around the stack issue, and they have other ways of dealing with the heap allocation issue. This is specifically, my comments were specifically about JavaScript, which is that JavaScript is getting around a stack problem but creating a heap problem. CPS is actually how languages like compilers in C deal with recursion in an optimized form. They don't necessarily rewrite it into a tail call form, they will rewrite it into a CPS form. And that's what the C compiler does automatically for them. So they have other techniques for dealing with the memory allocation problem there. But for us, the problem, because they're not dealing with closure there like we are, they're doing it in a different way. We're dealing with closure, which is allocation off of the heap, so we have a memory problem that we have to deal with.
What are good trampoline libraries?
Oh, you don't need a trampoline library. Trampoline is a utility that will be provided to you by your favorite functional programming library. Lambda has one, Lodash has one. Almost all the functional libraries will have that utility that you just pass it in. They may have slightly different quirks for how they work, so read the documentation, but they basically all provide this because it is generally one of the accepted or preferred forms for doing recursion when you can't take advantage of tail call.
And can you summarize the difference between trampoline and regular recursion?
Yes. The difference between a trampoline call, like what we see here, and regular recursion is that in regular recursion, we stack up the work. We literally stack up the work. We say, you do some work, and then you do some work, and 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 that's growing our memory size. In a trampoline, we never stack up the work. We do some work here, and then we return work back to this helper, this utility called trampoline, by way of returning the function. That's what we're doing in line 5. We return a function. And then the trampoline says, you return me a function, I need to do that work. And then we return some more work, and then we do it. And so we're bouncing up and down between a stack depth of 0 and a stack depth of 1 over and over and over again. We're not stacking up. And that's the difference. That's how we avoid that range error. So just as by way of one final comparison, let's put the two implementations of count vowels next to each other. I just want you to see that it's not actually all that scary writing a trampolinable recursive function versus a non-trampolinable version. In the first version up on top, we have a function count vowels, which is tail call form. And then in the version on the bottom, we have a trampoline version of it. And if you notice, line 4 on top and line 2 on the bottom, they're the same line. Line 5 on top and line 3 on the bottom, they're the same line. Line 6 on top and line 5 on the bottom, they're the same line. So those are exactly the same pattern. You can write a tail call form function, and then all you have to do is insert that wrapper function, line 4 and line 6 there at the bottom, insert the wrapper function to return that work and pass it to a trampoline.
So CPS.
All right, moving right.
All right, that was a lot, but the TLD of this is that if you want to use now if you want to use recursion in a memory optimized way, aka without calling all of these functions over one another, all of them. If you want to use recursion, which is something that you might need to go, especially if you're trying to traverse unknown length of data structure, makes a lot of sense in JavaScript. So by using this particular technique, which is the proper tail call, which is
So CPS is recursion.
Yes. The difference between a trampoline call, like what we see here, and regular recursion is that in regular recursion, we stack up the work. We literally stack up the work. We say, you do some work, and then you do some work, and 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 that's growing our memory size. In a trampoline, we never stack up the work. We do some work here, and then we return work back to this helper, this utility called trampoline, by way of returning the function. That's what we're doing in line 5. We return a function. And then the trampoline says, you return me a function, I need to do that work. And then we return some more work, and then we do it. And so we're bouncing up and down between a stack depth of 0 and a stack depth of 1 over and over and over again. We're not stacked.
But it's because with the trampoline, what it's doing is that, hey, you return me a function, then I'm going to call you that function for that. And then because you are calling is a function, is now going to call that function. That's interesting. Hey, you give me now a function here, okay, then let me now call that function for you. And then,
I need to do that work. And then we return some more work. And then we return work back to this helper, this utility
exactly, when you return the work back
called
to this
Trampoline,
helper,
by way of returning the function. That's what we're doing in line 5. We
so by returning the function, you're telling the Trampoline, hey, I
return a function.
returning function.
And then the Trampoline says, you return me a function, I need to do that work. And then we return some more work, and then we do it. And so we're bouncing up and down between a stack depth of 0 and a stack depth of 1 over and over and over again. We're not stacking up. And that's the difference. That's how we avoid that range error. So just
and not only how do we avoid the range error, because we also are doing is this proper tail calls, or the idea of being of the idea of memory efficient when we do a recursion by only calling is a function at the last position of that, and only that position. So it makes a lot of sense. It makes a lot of sense. It's maybe quite how do you call it? Yeah, something that you need to put at practice. Definitely something that you need to put at practice. But the whole point of this is that as long as you know that that technique exists, it will be much more easy for you to understand that later on, and so on and so forth. So that'll be all for this video. Take care. Bye bye.